Good morning. Good afternoon, everyone. It's my pleasure to do my presentation at this conference. Today, I'd like to talk about simplified elastic procedure for strain amplitude determination of nuclear safety class 1 piping on the seismic order. Okay, this slide presents overview of my presentation. First, introduction. Second, simplified elastic procedure, and the application of the simplified procedure to target model, and the seismic analysis result, and the compare result, and last, I will show conclusion. Okay. As you know, it has been reported that some beyond the design basis mistakes have occurred in Japanese nuclear power plants, such as Fukushima nuclear power plant. BDB means design beyond the design basis mistake. In response to these BDBs, Japanese nuclear regulatory body NSC issued NSC required 1-PS-1.02 for seismic design, considering BDB and plus strain. In addition, IAEA assigned BDB as a design intent condition. Nowadays, ASME, Boiler and Pressure Vessel Code Committee, has been organizing and operating some working groups related to BDB. In addition, recently, one seismic event beyond the OBE occurred in Gyeongju area in South Korea. OBE means operating basis of earthquake. So, Korea Nuclear Society has begun to increase interest in seismic safety margin of a nuclear power plant. Okay. As a part of these interests, Korean government announced that it would upgrade safety performance to 0.6G by 2023. So Korean nuclear industry, until now, Korean nuclear industry have performed this safety design for 0.6G plant using stress-based assessment and the response spectral analysis. As you know, however, this procedure has excessive conservatism. So, Korean nuclear industry tried to achieve this goal by performing seismic performance evaluation in plant level, such as seismic margin analysis or seismic PSA. As you know, this seismic performance evaluation cannot access safety margin in component level in more detail. So we needed to develop strain-based elastic seismic analysis technology to evaluate the seismic safety margin in component level. This figure shows present characteristics and the problem of the previous methodology present in SME Boiler Vessel Code Section 3 and characteristics of new methodology. From this table, we can see that new methodology considers the cyclic stress strain behavior and press strain and fatigue as a principal failure model. Time history elastic plastic seismic analysis considering plasticity, cyclic plasticity should be performed to apply the strain acceptance. However, it takes too long time, very long time, to perform the time history elastic plastic seismic analysis. In my opinion, this this time history, elastic plastic analysis is impractical from the viewpoint of engineering. So we needed to develop a simplified elastic plastic seismic analysis based on the previous elastic seismic analysis result and the penalty factor presented in the ASME pressure vessel code. Nowadays, the ASME code present only a simplified elastic pressure analysis procedure and penalty factor for low cycle fatigue analysis of level A and level D. Level A means level A events are corresponding to the normal operation transient. Level D events are corresponding to the offset operating transient. Okay. Purpose of our study, my study is to propose a simplified elastic pressure seismic analysis procedure based on the previous elastic seismic analysis result and penalty factor for strain determination of nuclear safety class 1 component, especially piping on the seismic road. Okay, this slide explains the penalty factor KE present in the ASME code section 3. Penalty factor KE can consider plastic strain occurring with the low cycle fatigue region. This figure shows a conceptual explanation of KE. We can define the KE as the ratio of SPE to SE. SPE means actual pseudo elastic stress. SE means stress, alternative stress based on elastic analysis. This figure shows penalty factor K equation present in the ASME code. Okay, this slide presents some penalty factors in the ASME code case and -779. SA means alternating stress. This parameter is considered as your input to perform fatigue analysis. SA equal KE SP minus SB minus AL plus KN, KN, SSB plus KU, SSL. SP minus SB minus SL means alternating stress. Considering primary membrane and bending stress and secondary membrane stress. SSE means secondary bending stress component. SSL means local peak stress component. KE is for primary membrane bending and the secondary membrane stress intensity. The Poisson ratio correction factor K2 is for secondary bending and local stress intensity. The Notch strain correction factor Kn is for secondary bending stress intensity. These figures are for K2 and Kn. This slide explains total alternative stress intensity for level A and B events for piping present in the ASME code section, subsection MB 3600. SP means total stress intensity amplitude. So first term is primary membrane stress component. Second term it means primary bending stress. This term is secondary bending. That term is secondary membrane. Last term is local peak stress component. Okay. In addition, ASME code subsection MB presents primary stress membrane bending stress intensity for level D event as follows. ASME code subsection MB 3600 presents secondary stress membrane and bending stress intensity for level D event as follows. PD means design pressure. design pressure. DO means outer diameter. ME means inner moment range due to inertia, seismic inertia loading. FAM means seismic anchor motion, axial loading due to seismic anchor motion. MAM means moment range due to seismic anchor motion. Level D events are corresponding to emergency or halted condition. Okay, this slide present calculation procedure of plastic strain amplitude. First, by using the previous elastic seismic analysis result and the penalty factor in the SMA code case and 779. Second step, by using the total alternative stress intensity equation and considering each stress confronted during seismic event, like these equation. Last step, by applying Hooke's law, we can derive the following equation. Okay, this slide presents the schematic configuration and the material of the target model. We consider the target model. We consider the pressurized surge line nozzle in OPR 1000 as a target model. This table, material property, physical property, and Chavez combined hardening model. Okay, this is we consider the inner pressure of 50 megapascal. This figure shows displacement time history with baseline correction for each support. This is we use the hybrid finite model consisting of beam element and three-dimensional break incompatible finite model. We have performed dynamic time history seismic finite element analysis by using abacus. Okay, we consider the Rayleigh damping. This is equivalent plus strain distribution. As shown in this figure, we can see that maximum equivalent plus strain occurs at this elbow. This figure shows equivalent plus strain history. As shown in this figure, it is found that maximum value of equivalent plus strain is 0.155%. Minimum value is 0. Okay, so we can calculate the equivalent plus strain amplitude as follows. Alternative plus strain amplitude is equal 0.0775%. This is the application result of the proposed analysis procedure. We use the beam element. This is maximum values of ME, FAM, and MAM by performing the finite element elastic seismic analysis. This figure shows calculation result by the proposed analysis procedure. From this table, it is identified that alternating strain value is 0.0789%. Okay, this table presents a comparative result of equivalent plus strain amplitude between the proposed analysis procedure and the detailed finite element elastic plastic analysis. So, from this table, we can see that there are very good agreement between two analysis procedures. Okay, conclusion. First, based on the previous elastic seismic analysis and the penalty factor in the SM code, we proposed the simplified elastic seismic analysis procedure for strain determination of nuclear safety critical piping on the seismic load. Second, when applying the procedure to pressurized surge line piping and comparing with the detailed finite element elastic seismic analysis result, we found that the proposed procedure can drive the good agreement. In the near future, we will extend the procedure to components such as pressure vessel, such as pressurizer, and so on. Okay, thank you very much.